The impossible proof. Our universe is a black hole's interior. Every photon you've ever seen might already be past a point of no return. The edge of our sky, the cold microwave afterglow we treat like a wall, acts like a horizon. A young researcher notices the map's edge behaving less like distance and more like a boundary that edits what we can know. If that's true, our cosmos isn't open space, it's a trapped interior. The Big Bang still explains a lot, but stubborn glitches remain. Flatness, horizon, initial conditions. One theory turns those glitches into fingerprints. To see why the edge looks like a horizon, we need to go back. The comfortable story with cracks. We got used to the origin story that works. A hot, dense beginning. Space expanding, cooling, making light nuclei in the first few minutes. Billions of years later, stars cook heavier elements, galaxies gather, and the leftover radiation from that early plasma drifts through us at 3 degrees above absolute zero. The Big Bang didn't win by charisma. It won because it called its shots. It predicted the cosmic microwave background before we built the devices to see it. It told us how much helium and deuterium should exist, and telescopes found the right amounts. It gave us an expanding universe that lined up with galaxies drifting apart. But when the model pauses, 3 hairline cracks show up in the glass. The first, flatness. Today, space looks almost perfectly flat on large scales. That sounds normal until you realize how unstable that is. If the early universe had even a tiny bit too much or too little curvature, that deviation would have blown up over time. For it to be this flat now, the initial curvature had to be tuned to a ridiculous precision. If you hate miracles in physics, you feel the itch. Second, the horizon problem. Look at points on opposite sides of the sky. Their microwaves have nearly identical temperatures, as if they agreed on a number. But in the standard timeline, those regions were never in contact. No time to exchange heat, no conversation across the void. Yet they match to 1 part in 100,000. It's like 2 strangers waking up in different cities wearing the same sweater, same size, same loose thread on the cuff. Third, magnetic monopoles, the heavy relics some grand unified theories expect. If they were made in the early inferno, they should be everywhere. We don't see them. So the standard story added a clever prequel, inflation. A brief, frantic growth spurt that stretches space faster than light speed and irons out wrinkles. It pushes away unwanted relics, flattens curvature, and lets once neighboring regions imprint the same conditions before being ripped apart. Inflation is brilliant. It explains a lot and, in many versions, even seeds the tiny quantum fluctuations that become galaxies. But brilliance isn't immunity. To get inflation started and to end it in the right way, you still need specific conditions. Which potential? Which initial state? Why did it begin at all, and why did it stop with the right timing to leave us this cosmos? Some versions run into measure problems. If inflation never really ends globally, how do you define probabilities in a multiverse that never settles? We patched one fine-tuning with another kind of tuning and added a thorny statistical headache. Meanwhile, down a hallway lit by vending machines and grant posters, a graduate student stares at a fresh CMB uniformity map. The calibration pipeline scrubbed systematics all night. The map looks boringly smooth, the most exciting kind of boring. She thinks, if causality never linked these patches, who sent the memo? She writes a note in the margin. Either early coordination or boundary rule. That's the emotional core. If our beginning needs a perfect coin toss, our story feels incomplete. We crave a mechanism, not a coincidence. Here, the quiet hint. Black holes produce inside their horizons the very conditions we fight to explain. High density, a horizon that sorts information. Regions that can look flat in the right slices. A limit to what can talk to what, enforced by geometry, not plumbing. Get this, what if the fix isn't before the bang, but outside it? Not a new field in our past, but a new view of our place. Imagine our observable limit not as the edge of a balloon, but as the inside of a boundary that acts like an event horizon. In that case, the puzzles become the footprints you'd expect. Flatness stops being a miracle and starts being a property of how interior slices look. Uniformity stops being a conspiracy and starts being what happens when initial data comes off a boundary that already correlates the whole interior. This isn't about throwing out observations. It's about reinterpreting geometry while keeping every hard-won measurement. If the cosmos we see is the interior of something that formed in a larger environment, then causality, not convenience, draws the line around us. The stakes are personal. If there's a horizon, then some galaxies are never reachable by any effort we mount. Some futures are sealed off not by budget or politics, but by spacetime itself. And if the edge is real, then the laws we infer inside are partly a story about that edge. There's a reason physicists keep peeking over the fence. Black holes are the best laboratories for horizons, thermodynamics, and information. When we found out that their entropy scales with area, not volume, we learned that boundaries matter more than our guts insist. Our universe has a boundary of sorts too, an observable limit that behaves suspiciously like one. The more precise our maps became, the clearer the pattern looked, and the louder the question grew. Flatness, horizon, relics, 3 cracks in a window that still shows the world. Inflation taped the glass and in many ways made it hold. But the tape pattern is elaborate and the window keeps flexing where you least expect. If a different frame explains the straightness, the matching panes, and why some drafts never stop, maybe it's time to try it. The edge of everything might not be where we thought, and it might not be an edge at all. The black hole cosmology idea. To see why the edge looks like a horizon, we need a different map. Start with the core claim. Our observable universe could be the interior of a black hole that formed in a larger, older cosmos, not metaphorically, geometrically. In that picture, what we call our edge isn't a wall sitting out at some distance. It's a causal boundary, the same kind of one-way surface that defines a black hole. Inside it, time and space trade roles in strange ways. Densities soar near the beginning, and yet, to observers like us drifting with the cosmic flow, slices of space can look remarkably flat. Map the pieces carefully. The event horizon in the parent cosmos becomes the limit beyond which signals in here can't be influenced by anything out there. Our observable limit behaves like that. Beyond a certain distance, even light launched now will never reach us. The singular core, the place general relativity says curvature becomes infinite, corresponds to our earliest, highest density epoch. We're not replacing the Big Bang successes, we're reframing the geometry that delivers them. This idea didn't appear from nowhere. Bits of it trail through decades of work. The holographic principle, sharpened by Raphael Bauso and others, insists that in gravitational systems the information content scales with area, not volume. Black holes taught us this with the Bekenstein-Hawking entropy formula. If boundaries count more than guts, a universe with a horizon starts to look like a boundary-driven information system. Meanwhile, proposals from people like Paul Steinhardt's Critics and Alternatives and Lee Smolin's Cosmological Natural Selection flirted with a related picture. Black holes might bud off new universes with slightly varied constants. That's a selection story, not a proof, but it puts the nursery in the right place. There's another thread. Gravitational collapse generically forms horizons, and the interior metric of realistic black holes, rotating, charged, embedded in an expanding background, contains regions where space-like slices admit near-flat geometries. You don't need a miracle, you need the right foliation. In other words, what looks precariously tuned in a free-floating early universe can look typical on the inside of a horizon. The flatness puzzle loses its sting when flat-looking slices are a natural choice for comoving observers. Here, as what nobody knew at the time inflation took center stage. The price you pay for adding a new field and a new epoch is fine-tuning of a different sort. The black hole interior view shifts the burden to causality. If the edge is an event horizon, then the uniformity across the cosmic microwave background can emerge from data set on a boundary that already correlates the interior. You don't need opposite sides of the sky to shake hands. You need them to inherit conditions from the same surface. But there was one problem. People worry about the word singularity. If we're inside a black hole, do we hit a crunch? Several approaches, loop quantum cosmology bounces, non-singular interior models, ekpyrotic-like compressions, propose that quantum gravity smooths the would-be singularity into a bounce or a finite-density start. That's not established fact, it's an active area. The point for our story is narrower. The black hole interior supplies the right stage for high density, a horizon, and correlated initial data without demanding a cosmic coin toss. Let's be precise about stakes. If this reinterpretation holds water, the edge of our universe isn't a distance we'll reach with bigger rockets. It's a causal barrier written into spacetime. Some galaxies are not merely far, they're fundamentally inaccessible. Meanwhile, features that looked coincidental in the standard view become fingerprints of interior geometry. Flatness, uniformity, even certain large-angle anomalies in the microwave sky, all start to look like boundary effects rather than ad hoc patches. Key thinkers scattered along this path help anchor us. Bauso's covariant entropy bound frames what information a horizon can hold. Smolin's cosmic natural selection offers a speculative mechanism. Universes born from black holes inherit parameters, with those producing more black holes becoming more common. Others have explored interior slicings of Schwarzschild and Kerr geometries and their relation to cosmological metrics. None of these alone proves we live inside a black hole. Together, they sketch a blueprint that reinterprets, rather than rejects, our measurements. A natural worry is whether we're swapping one untestable story for another. But this isn't a shrug. It makes contact with numbers. Interior horizons imply specific causal structures. Boundary-driven initial conditions constrain the pattern of fluctuations. Horizon thermodynamics hints that cosmic acceleration could be an emergent pressure from degrees of freedom living on a boundary, not a mysterious fluid in the bulk. We'll stress test all of that against supernovae, baryon acoustic oscillations, and the microwave background, because any viable picture has to pass the same gauntlet as lambdictum. For now, hold the map in your head. Event horizon as observable limit, early high density as interior core, flat-looking slices as a natural foliation for comoving observers. If that's the geometry, then flatness is more than plausible, it's expected. And if the boundary correlates the interior, uniformity stops needing a meeting that never happened. Numbers are about to start cornering us. Flatness is just the first nudge. Uniformity is the gut punch. Fingerprint 1. Flatness without a miracle. This is where numbers start to pin us to the wall. Cosmologists wrap it in symbols, but the itch is simple. Space today looks almost perfectly flat. That means triangles add to 180 degrees on the largest scales. Light rays travel as if the cosmic fabric is uncurved, and the parameter we call omega total hovers painfully close to 1. In the standard framing, that's not neutral, it's unstable. Any tiny early curvature should have amplified over time, tipping the whole universe toward rapid recollapse or runaway openness. To land this close to flat now, the initial value had to be set absurdly close to perfect. On a whiteboard, it shows up inside the Friedman equation. The expansion rate squared tracks what's in the universe: matter, radiation, dark energy, and a curvature term that's divided by the scale factor squared. Roll the clock back, and that curvature term tries to dominate unless it was nearly zero to start. In practice, it means at a fraction of a second after the Big Bang, the deviation from flatness had to be 1 part in many trillions. If that sounds like balancing a pencil on its tip in an earthquake, that's how it feels. Inflation came in as the elegant fix. Stretch space by an enormous factor, and any initial curvature gets ironed flat. The same trick smooths out inhomogeneities, and with quantum jitters frozen in and stretched, seeds a nearly scale-invariant spectrum of ripples. But now you've traded one question for another. What set up the inflattened field, the shape of its potential, and the exact conditions that let it start, run long enough, and end gracefully? The pencil is no longer balancing after 1 second. It's balancing on the layout of a field you can't see, With parameters you choose to make the math behave. Here's the twist the black hole interior view brings. Inside a horizon, the way you slice spacetime matters. For observers who drift with the interior flow, there are natural choices of spatial slices that look flat even though the full geometry is wildly curved. In the interior of a Schwarzschild or Kerr black hole, certain constant-time surfaces that comoving observers would call space right now can be foliated to appear spatially flat to those observers, because the strong curvature is encoded in how those slices evolve, not in their instantaneous shape. That's more than a mathematical parlor trick. It means that near flatness on the slices we sample, our cosmic time surfaces, needn't be a fragile miracle. It can be a built-in feature of living inside a horizon. The curvature is real, but it's packed into the time direction and into the causal structure, not into the three-dimensional geometry we measure at a fixed cosmic time. What looked like a precarious dial setting in a freestanding early universe becomes a natural perspective effect of interior geometry. A small group met to puzzle this out in a cramped office, windows fogged by winter breath. One of them drew the usual FLRW line, another layered in interior coordinates from a black hole metric. The room got quiet when the flat foliation dropped out with no finger-on-the-scale assumptions. Someone said, "If the slices we live on want to be flat in here, maybe we've been worrying about the wrong miracle." The board filled with arrows. Inside horizon implies foliation freedom, implies observational near flatness without tuning. Pause on stakes. This is not a free pass to ignore data. We still measure curvature through the sum of omega values using the microwave background's acoustic peaks, baryon acoustic oscillations, and lensing. Those numbers keep saying flat within small errors. In the inflation picture, that's a win because stretching kills curvature. In the black hole interior picture, it's a win because our observational slices naturally come out flat-like. Two roads, same signpost. The power here is that one road removes the need for a delicate starting point. There's a second payoff. The fine-tuning moves from initial conditions to geometry. We aren't begging the universe to begin almost perfectly flat. We're recognizing that for comoving observers inside a horizon, flatness is an emergent property of how you cut the spacetime. That makes flatness less of a coincidence and more of a diagnostic. If we saw strong, persistent curvature today, this interior picture would be in trouble. Seeing near flatness again and again is the nudge. Of course, the skeptic in the room raises a hand. Can an interior that's curved in 4 dimensions really hide spatial curvature from us? The answer is yes, and we already live with echoes of that idea. Think of de Sitter spacetime. You can write it with different coordinate choices, some that make space look flat, some closed, some open, all describing the same physical world. Geometry's story changes with slicing, but observables don't. The black hole interior adds a causal horizon that picks out which slices are physically relevant to us. This doesn't prove the case. It sharpens it. Flatness, once an argument for a rapid stretching episode, also fits an interior horizon where our clocks and rulers sit on flat-like slices by construction. We don't have to invoke a special roll of the cosmic dice. We have to take horizons seriously. And if flatness is just the first nudge, uniformity is the gut punch waiting on the other side of the board. Fingerprint 2, the horizon problem recast. Stand on a mountaintop at night and look east and west. The microwave glow you're seeing from both directions has the same temperature to 1 part in 100,000. In the standard story, those two patches never had time to talk before that light was released. No messages, no heat exchange, no shared past light cone. Yet they match like synchronized clocks. That's the horizon problem. Distant regions of the early universe look coordinated without causal contact. To feel it in your bones, we need 2 horizons on the table. The particle horizon tells you how far light could have traveled since the beginning until a given time, who could have ever talked to whom. The event horizon is about the opposite, the boundary beyond which signals, even if sent now and forever, never reach you. In the textbook Big Bang without inflation, the microwave sky's opposite points lie beyond each other's particle horizons at recombination. They shouldn't have equilibrated. Inflation fixes this by pushing tiny, well-mixed regions to cosmic scales, so patches we see far apart were once neighbors. The black hole interior view doesn't deny the geometry of light cones. It reframes the causal bookkeeping. Inside a horizon, causality compresses in a different way. Data that sets the interior's initial state can live on the boundary itself. If the edge of our cosmos is an event horizon in a parent spacetime, then much of what we call initial conditions is inherited from a single surface that already correlates the entire interior. You don't need opposite sides of the primordial plasma to exchange photons. You need them to be born from the same boundary prescription. Here, S where horizon crossing flips roles. In inflation, fluctuations start inside the Hubble radius, exit during rapid expansion, then re-enter later to seed galaxies. In a collapsing parent region that forms a black hole, modes can be driven the other way. Compression pushes wavelengths across an interior horizon, freezing correlations set by boundary conditions. When the interior later expands along its own time direction, those imprinted correlations ride the flow. The matching temperature across the microwave sky isn't a conspiracy. It's the echo of shared origin data. Boundary rule. That note on a grad student's printout wasn't a throwaway. Holography argues that the maximum information in a region scales with its bounding area. If that's the bookkeeper, then the early interior's degrees of freedom are not free to wander uncoordinated. They're constrained by a global ledger written on the horizon. From our perspective, that shows up as uniformity with slight, structured deviations, exactly the pattern we observe, a near-perfect blackbody with small anisotropies. Let's be concrete about signals. Picture light cones painted onto a spacetime diagram of an interior region. The past light cone of a point on the last scattering surface doesn't intersect the past light cone of a point on the opposite side, if you only consider bulk propagation. But if the state of that entire slice was fixed by boundary data laid down when the horizon formed, then those 2 points share ancestry through the boundary, not direct bulk conversation. It's a different way of threading causality. The bulk inherits, then evolves. There's an extra mechanism hiding in plain sight. Near a horizon, the redshifting and blueshifting of modes depend on surface gravity, a measure of the horizon's acceleration. If the parent horizon's properties set a temperature and a spectrum of fluctuations, then the interior gets a template for the variations we later measure. That's not a claim that Hawking radiation painted the CMB. It's a statement about boundary-imposed initial power. The spectrum we see could be a projection of horizon-encoded correlations. Meanwhile, in a dim control room, a CMB analyst stares at a sky map after another round of calibration has wiped out instrument quirks. The map is still too smooth. The tiny hot and cold spots are there, but the large-scale modes feel eerily quiet. Low power at the largest angles, odd alignments that statisticians argue over. She rubs her eyes. If the early plasma obeyed simple bulk causality alone, why do the biggest patterns look like someone gently pressed flat? She writes edge imprint in the margin and circles it twice. Skeptics jump in quickly. Uniformity from a boundary sounds like magic unless you show the math. Fair. The math lives in how you set initial conditions for fields in a spacetime with a horizon. Holographic ideas like Boussow's covariant entropy bound constrain what can be stored and how it's distributed. In practice, that means the interior's quantum fields can start in correlated states that respect the boundary's limited information capacity. When those fields couple to photons and baryons, the result is a plasma whose temperature is astonishingly even, before any bulk equilibration. There's a crucial difference in tone here. Inflation is a dynamical cure. It does work to smooth and stretch. The interior horizon view is a kinematic cure. It limits what initial states are allowed and correlates them at birth. Both can generate a nearly scale-invariant spectrum with small deviations. Both concede the acoustic peaks we later measure. The payoff for the interior story is economy. You get uniformity without a separate era that needs finely chosen potentials and exit strategies. Importantly, this recast horizon story is falsifiable in spirit. If future maps found strong, unambiguous signatures of regions that never shared boundary ancestry, clear, inconsistent patches that demand local, late-time equilibration, we'd be in trouble. Instead, the sky keeps whispering one message: uniform with structured global correlations. The boundary did the talking, and the echo of that talk is still cooling through us. The holographic playbook. If the boundary did the talking, we need to learn its language. Start with a rule that black holes forced on us: information scales with area, not volume. Jacob Bekenstein guessed it. Stephen Hawking's calculation, entropy equals a quarter of the horizon area in Planck units, locked it in. That was a slap in the face to intuition. We expect bigger rooms to hold more secrets. Gravity says, count the wallpaper, not the floor. Gerard T. Hooft and Leonard Susskind translated that shock into the holographic principle. A region's physics can be encoded on its boundary like a projection. Holography isn't a metaphor stapled onto gravity. It's a bookkeeping law that keeps quantum mechanics and spacetime from tearing each other apart. Raphael Bausa sharpened it with a covariant entropy bound. For any light sheet flowing inward from a surface, the information passing through can't exceed the surface's area. In plain terms, horizons ration information. If our cosmic edge behaves as a horizon, the rationing starts there. Bulk fields can't start however they like. Their initial states must fit the boundary's limited ledger. That flips how we think about the universe's census. Instead of asking how much stuff the volume can hide, we ask what the boundary can store and how the interior reads it. The implication is radical and oddly practical. Many puzzles in the bulk are really questions about boundary bookkeeping. If the early interior looks uniform, maybe the boundary wrote a short, efficient script, one that leaves little room for wild, uncorrelated deviations. Now there's a thorn. Our large-scale expansion looks de Sitter-like, with a horizon that has an associated temperature. Does holography even work cleanly in de Sitter space? We don't have a finished theory, but there are sketches. The DSCFT idea, inspired by AD-SCFT's hard success in anti-de Sitter space, suggests a correspondence between a bulk with positive cosmological constant and a conformal field theory living on a boundary at future infinity. It's not settled, yet it points to the same moral: bulk gravitates, boundary counts. Meanwhile, horizon thermodynamics keeps nudging us. Assign a temperature to horizons. Hawking did for black holes. Gibbons and Hawking extended it to de Sitter. Assign an entropy proportional to area. Press on the horizon with matter and energy, and the first law of thermodynamics looks like Einstein's equations. That's Ted Jacobson's punchline. Gravity might be an equation of state, arising from microscopic degrees of freedom you don't resolve. If so, the cosmic push and pull we feel could be emergent, with the horizon's bookkeeping acting like a thermostat. Here's where it folds back into our story. If a horizon encodes the interior, then patterns we measure in the cosmic microwave background, its power spectrum, its polarization, are constrained by boundary rules before any bulk dynamics gets to sculpt them. Anomalies that bug people, low power on the largest scales, curious alignments, might be boundary fingerprints, signs that the ledger capped variance on the biggest modes. In a purely bulk story, those look like statistical flukes. With holography, they look like the edge doing its job. Skeptics ask for concrete predictions, not poetry. Fair. Holography has given those in other arenas. The AD-SCFT dictionary computes transport in strongly coupled plasmas, matches quasi-normal mode spectra, and reproduces entanglement entropy with the Ryu-Takayanagi formula. Minimal surfaces in the bulk calculate boundary entanglement. That last one matters. Entanglement isn't a side character, it's the glue of holography. If the boundary's entanglement pattern defines which bulk geometries are allowed, then the early universe's allowed ripples are already filtered by an entanglement structure that respects area law limits. Pull the camera in on a human moment. A young theorist squints at a matrix of correlations, CMB modes on one axis, spherical harmonics on the other. The matrix isn't random, it's whispering constraints. She overlays an area law model for entanglement across angular scales and watches the largest modes damp in a way that mirrors the data. No triumph, no press release. Just a scribble in the notebook. Boundary entanglement caps super-horizon variance. She doesn't sleep much that night. There's tension we can't gloss over. Holography in our universe is murky compared to its crisp sibling in negatively curved space. We're extrapolating a principle that's passed every test we can throw at it into a domain we don't fully control. But the pieces align in spirit and sometimes in equations. Horizons carry entropy. Entropy scales with area. Area bounds information. Information shapes the interior's initial conditions. Initial conditions set the sky. Projection is elegant. Expansion is messy. The next question cuts to the mess. Why is the expansion accelerating at all? If the edge keeps the books, maybe it also presses on the bulk. Dark energy through the black hole lens. Acceleration wasn't on anybody's bingo card. In the late 1990s, two teams of supernova watchers plotted distant type Ia explosions and found them dimmer than expected, too far for their redshift. The cleanest reading was brutal. The expansion isn't slowing, it's speeding up. Lambdictum took the hit and adapted. Add a cosmological constant, vacuum energy with negative pressure, and the equations fit. Supernovae, the CMB's angular peaks, baryon acoustic oscillations, weak lensing, they all point to a universe dominated by something that pushes. The success is real. So is the discomfort. The naive quantum estimate of vacuum energy overshoots observations by a ridiculous factor. If lambda is a property of empty space, why is it so tiny yet non-zero? Through the black hole lens, we ask a different question. What if the push isn't a fluid in the bulk at all? What if it's a thermodynamic pressure from the boundary's degrees of freedom? Horizon bookkeeping pressing on the interior. Horizons have temperature and entropy. De Sitter space, which approximates our late-time expansion, carries a Gibbons, Hawking temperature proportional to the Hubble rate and an entropy proportional to the horizon area. If the edge carries microstates and responds to changes in the interior, then the first law of horizon thermodynamics, energy flow equals temperature times change in entropy plus work terms, starts looking like Einstein's equations with a cosmological constant term emerging as a state variable. Entropic gravity sketches this mood. Think of gravity as an emergent thermodynamic effect tied to information storage on horizons. When matter crosses a Rindler or De Sitter horizon, information shifts. The horizon's entropy changes. The interior feels a force. Scale that to the whole cosmos. If our edge is a horizon, its microscopic accounting can manifest as an effective pressure. Not a new field, not a perfect fluid. Pressure because the boundary prefers certain configurations and resists others. That's philosophy unless it meets data. The good news is that the numbers it needs to hit are clear. Supernovae set a late time distance, redshift relation. Bow lock in a standard ruler anchored in plasma physics. The CMB pins the early geometry and matter content. Any boundary-driven acceleration has to reproduce the near-constant equation of state W approximately -1 across redshift, within small room for drift. A pure cosmological constant nails W equals -1 exactly. Observations to date hug that line, with mild hints of time variation hotly debated. A horizon thermodynamic origin can naturally sit near -1, because the edge's temperature and entropy change slowly as the Hubble scale creeps. Here, S where the interior story adds texture. In a black hole embedded in an expanding background, the notion of mass isn't isolated. It couples to cosmology. Some models predict that the effective gravitating mass of black holes scales with the expansion, not through accretion, but through how their interior solutions match the cosmic exterior. If black holes cosmologically couple, if their parameters drift with the Hubble flow, then a population of them can source an effective dark energy term when averaged across the universe. This is an emerging and debated proposal, e.g., Farrah et al. 2023-2024 Analyses, not settled science. It's an active, testable idea, but it points to the same moral. Horizon physics doesn't sit idle, it talks to expansion. Return to the horizon's temperature. In de Sitter space, Th/2 pi. As H slowly falls in matter-dominated eras and then asymptotes when dark energy takes over, the horizon's thermal character evolves. While this temperature isn't something we can directly detect as a radiative bath, if the boundary's microstates act like a thermostat, they can set a pressure that trends toward a constant at late times. The emergent acceleration would then be a property of the horizon's information capacity, and its response, not a bag of vacuum energy hiding in every cubic centimeter. We can even sketch a sanity check. Plug horizon thermodynamics into a Friedman-like equation derived as an equation of state, Jacobson's move. Small perturbations of matter across local Rindler patches reproduce Einstein's equations. Extend that to a global de Sitter, like horizon, and you get an effective lambda as an integration constant or as a state parameter fixed by boundary conditions. That isn't a calculation of the number we measure, but it reframes the fine-tuning. Instead of canceling quantum zero-point oceans to 60, 80, or 120 decimal places, you're asking why the boundary picks a particular saturation level for its entropy. It's still a why, but it's a different why. None of this excuses hand-waving. If boundary pressure drives acceleration, it must leave fingerprints. The integrated Sachs-Wolf effect, CMB photons gaining or losing energy as they pass evolving potentials, depends on the time variation of the expansion rate. Large-scale structure growth depends on how quickly matter overdensities deepen. A boundary-sourced push must match the observed ISW cross-correlations and the measured growth rate F sigma 8 within errors. So far, lambdictum does well with tensions H, S8, still unsettled. The interior view suggests a provocative angle. Those tensions could be boundary quirks, small shifts in how the edge's bookkeeping couples to the bulk at late times, slightly altering distance ladders or growth histories without wrecking early universe fits. A quiet moment in a seminar. Someone asks, if the edge sets the push, what sets the edge? That's the uncomfortable heart of it. In the interior picture, the horizon is inherited, born when the parent collapse formed the black hole. Its properties aren't arbitrary. They're tied to the parent's mass, angular momentum, and environment, then translated into interior parameters. If acceleration is a horizon property, then our lambda is a hand-me-down, filtered through interior dynamics and quantum smoothing. Strange, yes, but it trades an inexplicable bulk constant for a boundary condition with ancestry. Here's the payoff in plain words. Dark energy looks less like magic in the void and more like pressure from an information surface we can't cross. The push is the edge doing what horizons do, counting states, resisting change, and nudging the bulk toward configurations that respect its limits. If that's right, then the question shifts from, why is vacuum energy so small, to why does our horizon carry this entropy and temperature? That's a boundary question. And it points us to the next step. If the edge drives the push, what exactly is our edge? Our edge acts like a horizon. If the edge drives the push, we need to treat it like a real horizon, not a poetic metaphor. Start with what we can and can't reach. There are two limits that matter. The particle horizon is the bubble of everything whose light has had time to arrive since the beginning. It grows as more of the universe comes into view. The event horizon is crueler. It's the line beyond which even a photon fired today and tomorrow and 1 trillion years from now never reaches us. That one shrinks what's possible. It tells you what's forever out of reach. Our cosmos appears to have an event horizon because acceleration wins at late times. In a lambda-dominated future, the Hubble radius stabilizes to a constant scale, which behaves like a de Sitter horizon. That means there's a sphere, far beyond the galaxies we see, across which causality tilts one way. Signals can cross outward with the flow of expansion. Inward, they're redshifted into silence. That's exactly how a black hole's horizon works in reverse. Inside, you can fall in. Outside, you can't claw your way back. Different directions, same rule, one-way causality enforced by geometry. You can feel that horizon in the light itself. Photons from beyond a certain distance get stretched by expansion until their wavelength outruns any detector we could ever build. Redshift isn't just a color change, it's an energy drain. Near a black hole, climbing light loses energy to gravity and reddens. In our accelerating space, light loses energy to expansion and reddens. Two very different pictures, the same punchline. Horizons bleed information into undetectability. There's a temperature lurking at the edge. A stationary observer near a black hole sees a Hawking temperature set by the surface gravity, kappa, via T equals kappa/2 pi in natural units. A comoving observer in de Sitter space sees a Gibbons, Hawking temperature T equals h/2 pi, where h is the Hubble rate. Different settings, same structure. Acceleration builds a thermal bath. Even flat space does it if you accelerate. Unrus result. An accelerating detector clicks as if it's bathing in heat. Horizons and acceleration keep making thermometers lie in the same direction. That thermal character isn't trivia. It's a clue about information flow. A horizon with temperature and entropy acts like a membrane with microscopic degrees of freedom. When fields fluctuate across it, the horizon's bookkeeping updates. In a black hole, that update shows up as Hawking radiation. In de Sitter space, it shows up as a steady, low-temperature hum associated with the cosmic horizon. We can't collect that hum with antennas, but its existence tells us the edge isn't empty. It has a state. It resists change. It talks to the bulk through thermodynamics. Zoom back to galaxies. Some are already receding faster than light relative to us, not because they're moving through space, but because space between us grows. That's allowed. General relativity only forbids local superluminal motion. The cosmic event horizon marks the galaxies we will never influence or receive signals from, even if we wait forever. People sometimes ask, couldn't we just go faster? The answer is no. Rockets fight gravity. They don't fight geometry. The horizon's one-way rule wins. Here's a micro-derivation sketched on a napkin. In de Sitter space, the metric can be written so that the horizon sits at a fixed proper distance. R equals CH associate and entropy S equals A4, with A equals 4 pi R2 in Planck units. Associate a temperature T equals H/2 pi. Now nudge the energy inside by delta E, matter crossing the horizon or leaving it. The first law, delta E equals T delta S plus work terms, mirrors a Friedman-like relation between H and the energy density. The edge enforces a thermodynamic balance that the bulk has to respect. That's why horizon language keeps reproducing gravity's equations. It's not decoration, it's the ledger. Redshift dimming fits the same story. Surface brightness of distant galaxies fades faster than 1d2 because of two extra 1 plus z factors, one from photon energy loss, one from time dilation stretching arrival intervals. Horizons turn those into destiny. Past a certain z, adding more exposure time doesn't reveal more. It reveals less per unit rest frame time. That limit isn't instrument sensitivity, it's the geometry of the edge. Meanwhile, think about information. Drop a diary toward a black hole. For an outside observer, it signals redshift and time stretch until updates freeze on the horizon. In our universe, information from beyond the event horizon is effectively frozen for us. The boundary encodes what we can ever know. That's not a mood, it's a causal fact. It means our laws, as we infer them, are conditioned by the part of the universe whose light fits inside our ledger. There's a human moment tucked in here. An astronomer tracks a galaxy's spectrum year after year. Each new observation pushes the redshift a hair deeper as better instruments come online. One night she realizes the target's light is already so stretched that its future photons will be undetectable in any practical window. She writes in her notebook, "This is the last clean look. The edge just claimed another lighthouse." The parallel to black holes closes the loop. One-way surfaces with temperatures and entropies. Redshift that drains signal energy. A causal boundary that defines what counts as real for us. Our observable limits act like horizons because, in an accelerating interior, they are horizons. And there's a map on the sky that's most sensitive to what the edge allows. We've heard the whisper for years. Now listen to the echo structure. The CMB as a boundary echo. The oldest light is our earliest reliable diary. It left the primordial plasma when electrons finally let go and photons could fly free. That snapshot, what we call the cosmic microwave background, keeps the scars of every rule the early universe obeyed. Read it right, and you don't just see hot and cold spots. You see a ledger of who set the terms. Start with the triumphs. The CMB spectrum is a near-perfect blackbody. Its tiny temperature ripples, tens of microkelvin, aren't random snow. They organize into acoustic peaks in the angular power spectrum, the fingerprint of sound waves in the ionized plasma. Gravity pulled, pressure pushed, and modes of different sizes rang at different phases. Polarization adds another layer. Thomson's scattering at last scattering imprinted E-mode patterns aligned with those acoustic oscillations, while later gravitational waves would have left a faint B-mode curl we're still chasing. The damping tail, power dying off at small angular scales, tells you photons wandered and blurred the picture just before release. It's precision physics, and it works. Here's the twist. Similar musical structure can emerge if the initial notes come from a boundary rule. You don't need to claim the plasma didn't oscillate. It did. But what set the score it played? In the inflation story, quantum fluctuations of a field were stretched and frozen, giving a nearly scale-invariant initial power spectrum. In the boundary story, the horizon's information cap shapes which correlations the interior fields can start with. Give those fields the same plasma to play in, and they ring out acoustic peaks with phases and relative heights that look familiar. Different composer, same orchestra. We're not saying the origin is identical. We're saying the allowed initial conditions can be boundary-driven and still seed the same acoustic dance. That means the baryon loading that boosts the odd peaks, the matter density that shifts the peak positions, the radiation content that tweaks the early expansion rate, all of that remains. The difference hides upstream. Why the initial scalar power spectrum hugs a near scale-invariant form, why superhorizon correlations exist at all, and why the largest angular scales look a little quieter than a pure Gaussian draw would suggest. This is where anomalies stop being footnotes and start feeling like whispers from the edge. Low power at large angles, the quadrupole and octopole, has nagged since Kobe and WMAP. Planck nailed the measurement and the weirdness stayed. Alignments between those low-L multipoles, people call it the axis of evil half-jokingly, refuse to sink decisively into noise. The hemispherical power asymmetry, one half of the sky a bit louder than the other, shows up in some analyses. Inflation can live with these as statistical flukes. A boundary-limited story turns them into plausible fingerprints. If the horizon's entanglement structure caps variance on the biggest modes or correlates phases across the largest angles, you naturally damp and align the low-L sky. A CMB analyst knows the pain behind that sentence. Long days cleaning foregrounds, dust that mimics polarization, synchrotron arcs from our own galaxy, point sources that sparkle at the wrong frequencies, cross-checks between frequency bands, null tests that try to break the pipeline. And when the dust settles, the largest scales still look a bit too polite. She writes again, edge imprint, and underlines it harder. Let's talk power spectra without the alphabet soup. The pattern of ripples across the sky depends on three things: the initial conditions, how the plasma evolved, and how light traveled to us. The last two are boringly reliable. Boltzmann codes churn them out, matching everything from the first peak's position to the damping tail. The first piece, initial conditions, is where you choose your story. Inflation sets them with a vacuum picked for convenience and stability. A boundary story sets them by saturating an area law bound and distributing correlations through a horizon's entanglement network. Both give you nearly scale invariance with a slight tilt. Both predict Gaussian, adiabatic fluctuations to first order. Deviations live in details, non-Gaussian shapes, phase correlations, and the exact amplitude of the very largest modes. That's where tests sharpen. If the largest scales are suppressed because the boundary ledger can't carry unlimited variance, then the low L power cut isn't a coincidence, it's a cutoff. If phase alignments trace a boundary geometry, they might correlate with the dipole or with preferred axes tied to the interior slicing. If holographic constraints leak subtle, scale-dependent non-Gaussianity, its shape will differ from the template's inflation hunter's chase. None of this is proven. All of it is measurable in principle. There's a clean way to keep us honest. Don't rewrite what works. Keep the acoustic peaks. Keep the polarization cross-correlations. Keep the lensing deflection field that Planck reconstructs. Then ask, can a boundary-driven initial spectrum feed the same Boltzmann machine and land within current error bars, while improving the odds of the low L anomalies and any measured phase structure? If yes, the CMB stops being just a victory lap for inflation and becomes a stage where the horizon leaves fingerprints. We can't declare victory from a few curiosities, but the oldest light keeps pointing at a simple moral. The biggest patterns seem to know about a boundary. The echo we measure might not just be the plasma's memory. It might be the edge's first whisper, carried through sound and frozen into light. Stress tests, black holes versus observations. A story is only as strong as the numbers it survives. The interior horizon map sounds elegant. Now it has to thread the same needle lambdictum already threaded. We start with the supernova Hubble diagram, the distance, redshift curve drawn by standard candles. Type Ia supernovae don't care about our metaphors. They ask for a precise luminosity distance as a function of redshift. In lambdictum, that curve comes from a matter era giving way to a lambda-dominated era. In the interior picture, the curve must match too, because observers measure the same photons. The difference is where the push lies, in the bulk as a cosmological constant, or in the boundary as horizon thermodynamics. If the edge sets an effective equation of state near W approximately -1, the distance ladder tracks the same path within current errors. That keeps us in the game. Next comes the baryon acoustic oscillation ruler, carved into galaxy clustering by sound waves from the primordial plasma. BAU gives a standard scale we see at different redshifts, locking down the expansion history. A boundary-driven initial spectrum still seeds those waves. Their imprint in the late-time distribution of galaxies is then read through the same geometry. That means the comoving BAU scale has to sit where surveys find it. If horizon pressure drifts with time, the Alcock, Paksinski distortions and the angular radial split in BAU give us leverage. So far, a slowly varying, near-constant push stays compatible. Wild time dependence would be dead on arrival. Weak lensing and structure growth raise the stakes. Gravity doesn't just set distances, it sculpts clumps. Surveys measure how quickly matter piles up, summarized in parameters like F sigma 8. Lambdictum predicts a growth rate tied to the expansion history. The interior story can't tinker with growth freely. If the horizon pressure mimics lambda, growth remains close to the same track. Interestingly, the mild S8 tension, lensing preferring a bit less clustering than Planck's early universe fit, can be reframed. If boundary coupling slightly alters late-time potentials, you could shave growth without wrecking the CMB. That's a possibility, not a promise. It has to pass cross-correlations like lensing times CMB, galaxy times CMB, where the integrated Sachs-Wolf effect lives. ISW is a clean stress test. As CMB photons cross evolving gravitational wells, they gain or lose a bit of energy. Acceleration makes those wells decay, leaving an imprint on large angular scales that correlates with foreground structure. Lambdictum predicts a small positive signal. A boundary-sourced acceleration with the same effective W gives the same sign and similar amplitude. Deviations show up if the boundary's push changes more quickly than a true constant. Measurements to date find a signal consistent with lambdictum, with large errors. That leaves a narrow lane where horizon thermodynamics can run without being noticed, and suggests where to look harder. Then there's the H headache. Local distance ladders find a higher Hubble constant than early universe inferences from the CMB under lambdictum. The interior view offers a different angle. If the edge's bookkeeping couples to the bulk in a way that tilts late-time distances slightly, you can move the ladder and the anchor by tiny, redshift-dependent amounts. That's delicate work. You can't spoil the bow lock or the supernova sequence. But it hints that boundary effects might hide in calibration-like shifts rather than exotic new particles. Flip to S8, and the same story applies. Small late-time drifts in horizon, bulk coupling could ease growth without touching recombination physics. Honesty check. Where does the black hole cosmology picture struggle? Precision. It has fewer crisp, closed-form predictions than lambdictum plus inflation because holography in de Sitter, like settings, is incomplete. Without a finished DS-CFT dictionary, many calculations rely on analogies and effective arguments. Rotating, realistic black hole interiors matched to expanding exteriors are messy, so deriving an exact initial power spectrum from boundary rules remains a work in progress. And some claims, like cosmological coupling of black holes sourcing dark energy, are controversial and under active scrutiny. We need independent confirmation from lensing of black hole masses across time, quasar demographics, and gravitational wave population studies. That's why we Steelman the skeptic. Inflation, with all its measure headaches, nailed the phase and spacing of acoustic peaks and gave us a mechanism for near-scale invariant fluctuations. Occam's razor cuts in its favor. A single slow-roll field explains a lot with few parameters. The interior story risks parameter gymnastics if every anomaly is blamed on the boundary. The burden is clear. Don't just fit, predict differences. So what would separate them? Start with horizon-scale anomalies. If low-L power suppression and phase alignments persist and sharpen with better foreground control, a boundary cap on variance becomes more attractive. Look at the ISW. Precise tomographic cross-correlations can detect slight time dependence in the effective push that a true constant lacks. Non-Gaussianity offers another wedge. Inflation predicts specific shapes, local, equilateral, orthogonal, usually small. A boundary origin might leak a different pattern, tied to entanglement structure rather than field interactions. If future surveys find scale-dependent non-Gaussianity peaking near the largest modes with unusual phase correlations, that leans our way. Lensing by spectra and trispectra, how deflections couple modes, could also carry boundary fingerprints if the edge subtly modulates potentials. Falsifiability matters. If curvature is definitively non-zero at a measurable level, persistent across datasets, the flat foliation escape narrows. If B-mode polarization from primordial gravitational waves is detected at amplitudes natural for simple inflation, a boundary-only origin of initial power would be on the ropes unless it independently sources a similar tensor spectrum. If improved ISW tomography locks W to -1 with no redshift drift and nails growth to the lambdictum track everywhere, boundary couplings lose room. Strengtheners matter too. A consistent, predictive derivation of the initial scalar and tensor spectra from a concrete horizon microphysics model would be huge. Observationally, converging evidence that black hole parameters evolve with cosmic expansion in a way consistent with cosmological coupling would support the boundary, bulk dialogue. laboratory analog horizons showing robust information, thermodynamics relations that map onto cosmological signatures would help. The point of the stress test isn't to crown a winner today. It's to earn the right to keep telling the story. If an interior horizon can pass supernovae, bow, CMB peaks, lensing and growth while making better sense of the sky's largest scale quirks, and if it flags specific checkable deviations, then it deserves oxygen. Otherwise, it's a beautiful map of a country we don't live in. The information paradox reinterpreted. Physics hates lost information. That's the gut reason the black hole information paradox won't die. Stephen Hawking's calculation said black holes radiate like hot objects and eventually evaporate. But that radiation, taken at face value, is thermal, no memory of what fell in. If the hole disappears and the radiation carries no imprint, information is gone. Quantum mechanics forbids that. Unitarity says pure states evolve to pure states. Probabilities add to 1. Nothing gets erased. People fought the paradox from different angles. Some said information hides in correlations too subtle for Hawking's leading order result. Others built firewalls, hypothetical walls of high-energy quanta at the horizon that break the smoothness of spacetime to keep quantum bookkeeping honest. None of that felt comfortable. Then new tools arrived. Replica wormholes, geometric saddles and gravitational path integrals reproduced a page curve. The entropy of radiation rises early, peaks when the black hole is half evaporated, then falls to 0 when it's gone. That's what unitary evolution demands. The math said gravity, done carefully, can keep the books. Now thread our interior horizon map through this. If a black hole can preserve information through subtle correlations, why assume the information story stops at the horizon? In the picture where a collapsing region buds an interior cosmos, the degrees of freedom don't vanish, they reorganize. The boundary, our horizon, encodes, and the interior emerges as a way that encoding is realized. From the parent universe's perspective, information isn't lost. It's redistributed between radiation, boundary microstates, and an interior that, to us, is everything. Holography gives the language for that move. In holographic dualities that we actually control, de Sitter space tied to a conformal field theory, the boundary theory evolves unitarily. There's no place for information to disappear. Bulk processes that look lossy map to tidy rearrangements of boundary entanglement. If an analogous story holds even approximately for horizons like ours, then the right question is, where did the information go? In which degrees of freedom is it now stored? The boundary can hold an area's worth. The interior can carry the rest as emergent geometry. Here, where skepticism is healthy. We don't have a full DSCFT dictionary for our de Sitter, like world. The firewall debate showed how hard it is to satisfy every principle. No drama at the horizon, monogamy of entanglement and strict unitarity, at once. But the replica wormhole results change the tone. Gravity seems to know how to deliver a page curve without burning the horizon. The bookkeeping lives in quantum extremal surfaces, surfaces that pick out which chunks of spacetime count as radiation for entropy calculations. That's technical, but the punchline is simple. When you include the right regions behind the scenes, the entropy evolves exactly as if information never died. Translate that to a universe inside. If our cosmos is behind a horizon from a parent's point of view, then our fields and galaxies are part of the unitary ledger. The lost bits of a star that fell into the parent black hole aren't erased. They're encoded in the joint state of boundary microstructure and interior fields that, for us, became initial conditions and later structure. From our perspective, there's no paradox. Our world is the file. From the parent's perspective, the page curve survives because the encoding includes us. A human moment, because this gets abstract fast. A young postdoc stands at a chalkboard covered in entropy wedges and sketches of wormholes. She circles the part where the island prescription says you must include an interior region to compute the radiation's entropy correctly. She laughs, not because it's funny, but because the math forced her to add a piece of space she can't see to make the numbers honest. She writes, "Interior equals bookkeeping, not disposal," and takes a picture for her advisor. This reframing doesn't hand-wave away hard questions. It distinguishes what's nailed down from what's plausible. Nailed down, black holes radiate, horizons carry entropy, careful gravitational path integrals can reproduce the page curve. Plausible in our setting, a horizon with microstates can encode an interior. Unitarity is preserved by correlations that span boundary and bulk. The interior's emergence organizes information rather than destroys it. Speculative bridges, like a precise dual for de Sitter space, or an explicit map from a realistic collapsing star to a baby universe interior, are works in progress. But the moral is crisp. If horizons are accountants, not shredders, then living inside one isn't a threat to information. It's a guarantee that information has a home. Our measurements, our memories, the quantum seeds that grew into galaxies, all sit in a unitary story whose ledger runs along the edge. Information didn't go anywhere mysterious. It went everywhere we call here. Life inside, time, travel, and the endgame. If our world sits inside a horizon, time isn't just a line, it's a budget. Start with reach. The particle horizon grows as light from more distant regions finally arrives, but the event horizon tells us what's forever out of bounds. In a future ruled by acceleration, there's a sphere beyond which no signal we send, tomorrow or in 1 trillion years, ever returns. That boundary isn't a suggestion, it's geometry. Ambition meets a ruler that won't move. What does that mean for human futures? Interstellar travel stays possible, intergalactic migration doesn't. Distant clusters we can see today will slip past causal contact. Even within our local group, time thins options. The Milky Way and Andromeda will merge. Smaller companions will join the dance. Everything else fades into the red. A mission planner staring at a map in 2200 will face a real constraint. Launch windows measured not by fuel, but by cosmological time. Miss them, and targets drift from hard to unreachable. People ask about cheat codes. Wormholes live in our equations, but traversable ones demand either exotic matter that violates energy conditions or engineered spacetimes we don't know how to build safely. Inside a horizon, the rules get harsher. The geometry wants to funnel you inward in time-like directions. There's no secret route to outside. Even if you threaded a wormhole, both mouths would still sit within the same causal cage. Escape isn't on the menu. Navigation within is. Meanwhile, rockets face a quiet adversary, redshift and time dilation. Signals you send across megaparsecs arrive stretched and faint. A civilization trying to coordinate across the supercluster will find its messages losing energy, its reply cycles growing absurdly long. The practical outcome is a patchwork future, strong local webs, frayed long-distance ties. That isn't defeatist. It's a call to build deep roots, not just long lines. Here's a micro story. An astronaut in training runs the numbers for a probe to a galaxy now at redshift 0.5. She models the fuel, the sail, the beam. Then she adds the cosmology. The curve crosses a line. Even at light speed, the target's recession locks the rendezvous behind the event horizon. She closes the laptop and writes a different plan. Go smaller, go sooner. She didn't give up. She pivoted to what the horizon allows. Zoom way out. If we're inside an interior born from collapse, what's our endgame? Black holes in our cosmos will merge. Galaxies will exhaust star-forming gas. New stars will skew small and dim. Over trillions of years, starlight dwindles. Proton decay, if it happens, would dissolve matter on ridiculous timescales. If not, iron stars drift through a thin bath of photons. In a lambda-like future, space keeps stretching. Temperatures fall toward the horizon's thermostat, and islands of matter become lonely. Now the awkward question. Do interior universes evaporate like their parents? Hawking radiation shrinks black holes from the outside perspective, but from the inside, evaporation doesn't match a simple clock. If our horizon is de Sitter, like It carries a tiny temperature and a monstrous entropy. Its evaporation is the slow bleed of information through boundary microstates, not a countdown to a crunch. The interior can coast for eons, with its own arrow of time, while the parent's ledger trends toward balance. Our days aren't numbered in millions or billions, but the map still has edges. Mergers add drama. When supermassive black holes collide, they ring spacetime and settle into a larger, quieter whole. Inside our interior, those events reshape local neighborhoods, kicks that can eject stars, sprays of gravitational waves that warm the background by a whisper. They don't threaten the global horizon. They salt our long future with rare, shattering moments, like thunder in a thinning atmosphere. What about engineering the cosmos, nudging the boundary, manipulating horizons? The thermodynamic lesson bites. Horizons are stiff. You don't push them around without moving staggering energy across vast scales. Any attempt to bleach the vacuum or trigger phase changes carries risks we don't quantify. Responsibility starts with humility. Colliders won't crack the sky. Their energies are puny compared to astrophysical fireworks. Vacuum decay scares make headlines. Reality shrugs. Real risks live in the near field. Ecology, climate, resource cycles. Under a ceiling we can't lift. So where's the hope? Right where it's always been. In thriving within limits, fusion that closes the energy loop, recycling that turns scarcity into design, astronomy as memory, recording the galaxies while we can still see them, archiving star maps for descendants who will grow up under a dimmer sky, a culture tuned to long projects, cathedral thinking with engineering specs. There's a quieter shift too. Meaning stops chasing exits and starts tending gardens. If horizons define what counts as real for us, then our ethics bend toward stewardship of the interior. We can seed life across reachable systems, build networks that outlive single stars, and write libraries that survive carrier shifts as spectra redden. Ambition doesn't shrink, it narrows and deepens. The edge doesn't doom us, it focuses us. We won't escape the room, so we redesign the room light by light, ship by ship, law by law, until living inside feels less like a sentence and more like a craft. And once we accept we're staying, one question won't leave. How did this room open in the first place? Birth of a baby universe. If we're staying, how did the door open? Start with collapse. In a parent cosmos, a massive region runs out of pressure support and gives in to gravity. Horizons form first, a causal shell that seals off the interior. In classical general relativity, keep falling and curvature blows up. A singularity, the place where equations stop making sense. But that's the limit sign, not the road. Quantum gravity is supposed to repaint the sign. Several paths try. Loop quantum cosmology takes the discreteness of space seriously. Volumes come in quanta. When density climbs toward the Planck scale, gravity's attraction turns repulsive. Not everywhere, not forever, just near the would-be singularity. The result is a bounce. Contraction decelerates, halts, and transitions into expansion. The interior doesn't freeze in a point. It rebounds into a new, hot, dense phase that, to inhabitants, feels like a Big Bang without a start-of-time cliff. Another route is ekpyrotic-style compression. Instead of inflating, you smooth by squeezing. A slowly contracting phase dominated by a stiff equation of state ions out-wrinkles and kills anisotropy. In some models, a non-singular transition, mediated by new physics, links that contraction to expansion. The early universe's uniformity and flatness arrive not from stretching but from a long, careful compression. Inside a black hole interior, where horizons already corral causality, that script finds a natural stage. Real black holes rotate. That matters. Care interiors aren't simple funnels. They have rich structure, including regions where classical analysis predicts bounces across inner horizons. Classical instabilities likely wreck that neat picture, but they point to a theme. Rotation changes the interior flow. Add quantum corrections that regularize the core, replacing the singularity with a finite, high-density core, and you can thread a path from collapse to expansion without tearing the equations. Regular black hole models do this with modified stress energy at tiny scales, keeping curvature large but bounded. Skeptics ask what any of that buys us beyond aesthetic relief. Two things. First, it gives the interior a starting line with finite density and temperature, so nucleosynthesis, recombination, and everything we actually measure can play out as usual. Second, it hands you a mechanism for correlated initial data. If a quantum bounce happens under a horizon, the degrees of freedom that re-emerge into expansion inherit boundary-imposed constraints. Uniformity stops being a miracle and becomes a consequence of how the boundary stores information through the crunch. There's a selection idea that rides along, clearly marked as theory. Lee Smolin proposed cosmological natural selection. If black holes spawn universes, then the constants of nature might vary slightly between offspring. Universes that make more black holes, via star formation physics, cooling, nuclear reaction rates, would have more descendants. Over many generations, parameters drift toward values that favor copious black hole production. It's an evolutionary tale without a designer. Branching paths, differential reproduction, inherited traits with small mutations. It's intriguing because it links what we see, stellar life cycles, supernova thresholds, neutron star limits, to a larger genealogy, but it's not proof. Testing it would mean checking whether small tweaks to constants generally reduce black hole yields and whether our constants sit near local optima. Some checks exist, none close the case. Still, the frame flips how we weight coincidence. Fine-tunings that seemed spooky become selection biases in a population we can't sample directly. A different set of tests peeks through astrophysics. If black holes in our universe couple to cosmology, if their effective mass drifts with the Hubble flow, then their demographics across Redshift carry a boundary fingerprint. Quasar mass functions, gravitational wave merger catalogs, lensing of bulges at different eras, all become probes of whether horizons talk to expansion. If they do, that suggests the same conversation could have set the stage when our interior began. We need a human face on this. A core-collapse supernova simulation crashes on a cluster. The student reruns it with a slightly different nuclear equation of state, a stiffer core, a bit more neutron degeneracy pressure. The bounce shock holds longer, the proto-neutron star breathes differently, the fallback rate changes. On the screen, a black hole forms 10 milliseconds later. The student leans back, thinking about doorways measured in milliseconds and microphysics. She writes tiny changes, huge fates. Ethics sneaks in. If black holes can bud interiors, then every massive star's death might seed futures we'll never see. That weight isn't mystical, it's causal. Our engineering choices, how we nudge star formation in distant clouds, how we sculpt galactic environments, could tilt the number and kind of horizons that form. We don't know enough to act on that responsibly. But the possibility changes posture. Humility first, curiosity second, intervention a distant third. We also have to be clear about what's solid. Big Bang nucleosynthesis still pins light element abundances. The CMB still reads like a plasma diary. Large-scale structure still grows as gravity directs. The interior bounce picture doesn't rewrite those chapters. It rewrites the prologue. Instead of a singular beginning plus added inflation, you get a high-density start encoded by a horizon and possibly smoothed by compression or quantum repulsion. One more open loop. If our universe budded from a horizon, do black holes here host their own interiors? The math doesn't forbid a fractal family tree. It doesn't guarantee it either. Observationally, we'd be looking for indirect signs, consistency in parameter drifts, constraints from horizon thermodynamics, maybe even analog experiments where laboratory horizons mimic parts of the script. For now, it's a question we carry, not a flag we plant. The picture is audacious but grounded in a simple shift. Treat horizons as real, treat singularities as signs of missing physics, and let the boundary write the first page. Collapse becomes cradle, bounces replace breaks, and the room we live in might be one chamber in a nested house of many rooms, each lit by its own beginning, each bounded by its own edge. The ethical horizon. If collapse can be cradle and horizons can write first pages, our choices echo farther than we'll ever hear. That raises a hard question. How do we carry responsibility across a boundary we can't cross? Start with two ways people usually make meaning. One leans on anthropic reasoning. We observe a universe compatible with our existence because we couldn't observe any other. The other asks for selection. Maybe parameters were sifted by processes that favor universes that make more black holes, more stars, more observers. Neither gives permission to treat speculation as destiny, but both warn us that local actions can sit inside larger stories. We have to separate real risk from ghost stories. Colliders won't pop the vacuum. Their energies are dwarfed by cosmic rays slamming atmospheres every day. Triggering a universe in a lab isn't on the table. We don't control horizons. The risks we do own live close: biospheres, climate stability, energy loops. Cosmic engineering, nudging star formation, seeding clouds, building megastructures, sounds bold. It also drags unseen consequences. If black hole formation rates carry ethical weight because they might seed interiors, intervening in galactic ecology without a theory is hubris with a long fuse. So what does responsibility look like in a horizon-shaped world? First, honesty about uncertainty. Mark what's established: Big Bang relics, CMB structure, gravitational thermodynamics, and ring speculative bridges with bright tape. Second, proportionality. The nearer the feedback, the tighter the duty of care. If you can model the outcome, you can own the outcome. Third, patience. A horizon is a long-term contract. Projects that outlive founders, archives, seed banks, interstellar beacons, fusion infrastructures, fit a cosmos where reply cycles may stretch beyond a lifetime. Culture changes under a ceiling. Art learns to sit with distance. Paintings of fading clusters, novels where messages arrive as fossils, music written to be heard by descendants when the sky is sparser. Policy stretches its horizon too. Budgets that reward maintenance and quiet reliability, not only shiny launches. Education that teaches thermodynamics and ethics side by side. What a horizon allows, what it forbids, and why limits aren't enemies of imagination. There's a practical ethic for science as well. Build instruments that can be audited decades from now. Preserve raw data and calibration pipelines so the next team can rerun the sky with new questions. Share maps while we still have windows to paint them. If future astronomers live under redder light, our catalogs become their time machines. That's not romance. It's duty under entropy. Then there's humility. If universes can bud from horizons, our black holes might be someone's beginnings. That doesn't make us gods. It makes us gardeners with clumsy tools. Pushing star formation just to manufacture horizons would be ethics by body count. A better stance is restraint. Understand before you tinker. Accept that some levers are off limits until the theory matures, and prefer interventions that are reversible on human timescales. Skeptics will say we're wrapping metaphysics around engineering. Maybe, but horizons force a kind of honesty. You can't optimize what you can't reach. You optimize what you contend. Neighborhoods of stars, networks of knowledge, habits that keep systems stable against drift. Stewardship becomes less slogan and more operating system. One more human moment. A city council debates funding a deep sky observatory that will outlast their terms. A teenager at the microphone says, "We won't see all the galaxies, but someone will see more because we built this now." That's the ethic in a sentence. Build for people behind their own horizons, not because they'll thank you, but because someone did the same for you. Before we close, the strongest counters deserve their shot. If this story is only poetry, it will fail hard against data. Good. That's how we keep meaning welded to measurement. The skeptic's case and rebuttals. Start by giving the other side the microphone. Inflation earned its keep. With a handful of parameters, slow role models predicted a nearly scale invariant spectrum, adiabatic and close to Gaussian, and nailed the phase and spacing of the acoustic peaks. That's not hand-waving, that's a scoreboard. It also predicted super-horizon correlations that the CMB shows, and it gives a clean story for why curvature looks tiny today. If you're a working cosmologist, Occam's razor points to the model that already matches the data with the fewest moving parts. Critics of the interior horizon picture say it's pretty but slippery. Where's the concrete Lagrangian? Where's the closed-form initial power spectrum derived from a horizon microphysics we actually know? Where are the tensor predictions? They'll add that boundary did it, risks becoming a catch-all for every anomaly, and that without a precise DSCFT dictionary, holography in a de Sitter, like universe, is more compass than map. On dark energy, they'll say the cosmological constant fits every distance test so far. Why trade a constant for an emergent pressure unless you can compute the same numbers with the same precision? That's the Steelman. Now we answer without dodging. First, holography is an optional decoration. Horizons carry entropy, information-bound scale with area. Gravitational path integrals recover page curves when you include the right quantum extremal surfaces. Those aren't aesthetic choices, they're facts any complete theory must respect. If inflation sits inside a bigger holographic frame, that's fine. But a story that never asks where initial conditions live relative to a horizon is leaving money on the table. Second, we agree that ambiguity is a weakness. So we put markers on the ground, places where boundary-driven cosmology can diverge from inflation in measurable ways. Horizon-scale anomalies are the first. If low-letter 2113 power suppression sharpens, if quadrupole, octupole alignments persist after even harsher foreground cleaning, and if their phases tie to a boundary-selected axis rather than random chance, that's a signature inflation treats as fluke. A boundary cap on variance turns it into expectation. Third, tensors. Simple inflation links scalar and tensor power through the energy scale of the potential. If future B-mode polarization reveals a tensor to scalar ratio at levels natural for many slow-roll models, a pure boundary origin of structure takes a hit unless it independently produces comparable tensor modes with the right tilt. That's falsifiable. If instead B modes keep sinking below those thresholds, the pressure to adopt simple and flattened potentials eases, and boundary-filtered initial conditions stay alive. Fourth, non-Gaussianity. Inflation predicts small departures with specific shapes. A boundary origin can leak different patterns, especially at the largest scales where entanglement structure matters most. Look for scale-dependent, low-letter 2113 weighted non-Gaussianity with unusual phase correlations, rather than the standard local equilateral templates. Lensing bispectra and trispectra provide independent checks. A horizon that subtly modulates late-time potentials imprints distinctive mode couplings. Fifth, late-time growth and the integrated Sachs-Wolf effect. If the edge's effective pressure drifts slightly with redshift, ISW tomographic cross-correlations will tilt in a way a strict constant won't. At the same time, the growth rate F sigma 8 can shave low without disturbing the CMB's early anchors. That's a narrow lane. It can be closed by data. That's good. It means the interior horizon map has skin in the game. Now the razor. Is the interior story simpler? Not yet, not in equations you can fit out of the box. But simplicity isn't only parameter count. It's conceptual economy. If one horizon-based principle, area-bounded information, naturally explains uniformity near flat slices and the existence of a push that tracks de Sitter thermodynamics, that's a consolidation of puzzles into one origin. We're trading a tuned inflattened potential and reheating complications for a boundary condition with thermodynamic rules. It's a different place to hide the complexity, and we should be honest about that. The test is whether it hides less. We also put our neck on the block. What would kill this? A decisive detection of primordial tensors at amplitudes cleanly predicted by simple inflationary potentials and incompatible with any plausible boundary sourced tensor mechanism would be brutal. A robust, multi-probe determination of non-zero curvature at today's level inconsistent with flat foliation inside plausible interiors would corner us. ISW tomography that nails W to an unchanging -1 with no wiggle across redshift, while locking growth to the lambdictum track everywhere, would squeeze boundary couplings to irrelevance. And if low-letter 2113 anomalies melt away under next-gen foreground control, the boundary cap narrative loses its loudest whisper. What would strengthen it? A concrete predictive computation of the scalar and tensor spectra from an explicit horizon microphysics model that reduces to known holographic results in controlled limits. Independent evidence that astrophysical black holes cosmologically couple via redshift trends in mass functions, lensing of host bulges, and gravitational wave demographics would support boundary, bulk dialogue at late times. Laboratory analog horizons that reproduce information, thermodynamics relations mapping onto cosmological signatures would add weight. There's a tone check we keep. Inflation's wins are real. Lambdictum track record is solid. The interior horizon story isn't a replacement trophy held high. It's a pressure test on our assumptions about where initial conditions live and how horizons talk to expansion. If it passes the same gauntlet while demystifying the largest scale quirks and reframing dark energy as thermodynamics, it earns a seat at the table. If not, we step back. Either way, insisting that horizons be more than metaphors makes the science sharper. What we'd need to know next. If this story is going to graduate from elegant map to lived country, we need sharper coordinates. Start with the measurements that pinch the model now, H and S8. The H tension, early universe inferences versus late universe ladders, stays a crack we can probe. We need distance ladders with cleaner anchors, cross-checked by independent physics. That means parallaxes tied to Cepheids, masers that set geometric distances, tip of the red giant branch calibrations, and strong lens time delays with ruthless lens model systematics. If boundary couplings bias late time distances by a hair, that hair has to show the same bend across these methods, or the story breaks. S8 sits next to it, holding growth by the collar. We need weak lensing maps with lower shear biases and better photometric redshifts, cosmic shear times galaxy clustering cross-correlations that triangulate growth, and peculiar velocity surveys that taste structure without relying on light profiles. If late-time horizon pressure softens potential slightly, the data will show a coherent pattern, a small, scale-dependent shave in growth that stays consistent with CMB lensing and bow anchors. If instead every probe lands on the lambdictum growth track when systematics shrink, there's no room left to hide boundary quirks. Next, the CMB's polarization is our lie detector. The largest scales need a cleaner sky. We need next-gen EB separation with foreground control that doesn't flinch, multi-frequency coverage that deconfuses dust and synchrotron, half-wave plate modulation that kills 1F noise, and scanning strategies that cross-link the whole sky. If the low-letter 2113 anomalies are boundary fingerprints, they should persist in polarization in ways that match a cap on variance and phase structure, not just temperature chance. And B modes. If primordial tensors appear with an amplitude and tilt natural for simple slow roll inflation, a purely boundary-seated scalar spectrum has to grow matching tensors or bow out. If B modes keep sinking, boundary-filtered initial conditions stay in play. Large-scale structure non-Gaussianity is another lever. Standard templates, local, equilateral, orthogonal, are only part of the story. We need bispectrum and trispectrum estimators that can hunt scale-dependent, horizon-weighted shapes and phase correlations, especially on the largest modes where entanglement structure matters. That means huge volumes, careful window function corrections, and synthetic skies that stress-test pipelines. If a boundary origin leaks distinctive mode coupling at low-letter 2113, future surveys should catch the pattern across galaxy clustering, 21 centimeter intensity maps, and CMB lensing cross correlations. ISW tomography is the time dependence probe. Split the sky by redshift with deep galaxy samples, cross-correlate with CMB maps, and watch how the signal evolves. A true constant drives a specific redshift profile. A boundary-sourced pressure that drifts slightly should tilt that profile in a measurable way. This isn't about hand-waving a wiggle. It's about pinning a function with error bars small enough to pick a side. Now the theory bench. We need a clearer DS/CFT-like dictionary, even if it's approximate. Concrete examples where boundary unitarity and a positive curvature setting maps to bulk dynamics we can compute. That includes entanglement wedges and quantum extremal surfaces in de Sitter patches, and explicit calculations that derive scalar and tensor spectra from boundary microstates under area law constraints. We also need realistic interior slices of rotating black holes matched to expanding exteriors, with quantum regular cores that avoid singularities. The goal isn't a pretty cartoon. It's a pipeline from horizon microphysics to a power spectrum with numbers you can fit. Observationally, black holes themselves can testify. If cosmological coupling exists, black hole masses should drift with redshift beyond what accretion and mergers explain. That's testable. Track supermassive black hole, host relations across time with better bulge dynamics measurements, reverberation mapping, and high Z quasars. Use gravitational wave catalogs to watch the mass function evolve in the stellar mass range. Lensing around galactic centers adds another angle. A consistent trend across these lines would support boundary, bulk dialogue. A flat line would shut that door. Finally, analog horizons can stress the thermodynamics. Laboratory systems, Bose, Einstein condensates, optical fibers, flowing fluids, already mimic horizon kinematics. We need experiments that probe information flow across these effective horizons and measure entanglement entropy bounds in ways that can be mapped onto gravitational statements. It won't prove cosmology. It will test the robustness of the horizon as bookkeeper idea that underwrites this whole picture. None of this asks for faith. It asks for work that either tightens the interior story into a predictive framework or trims it back to metaphor. Better H and S8 constraints, sharper CMB polarization at large scales, non-Gaussianity with teeth, a DS-flavored holographic map, black hole demographics across time, horizon thermodynamics you can poke in a lab. That's the road. If we walk it and the edge keeps whispering the same story, then the room we live in won't just feel like a black hole's interior. It'll read like one. If the edge of everything is a horizon, we're living in the most astonishing escape room. One nobody escapes. If you want the next piece, how baby universes could inherit physics from ours, watch the follow-up. Subscribe for the untold stories hiding at the edge of science, and share this with a friend who loves impossible questions.